Okay, so compared to the last talk, my talk may seem very baby stuff, okay? Because usually I roam around K through 12, okay? So hopefully everything will make sense. So usually, in math, identities mean something like a plus b whole square equal to a square plus 2ab plus b square, but I hope you understand that here identity is in the more commonsensical way, right? I mean, you understand something, certain shapes in a certain way, and maybe, what I will be trying to do is twist it around, okay? So let's look at triangles first, okay? And usually we start with sidewise. So here's a question. This is how we learned it in school. Is this what you learned? Okay. Now, if you go online, this is what you will find now. Okay? If you think, this basically means there are two categories, and equilateral is a subcategory under isosceles. Okay? That's what it means. So, here's the question. Why is the new one better? Okay. See, what happened is, when our parents and our teachers were in school, they used to learn that square is not a rectangle. Okay? But when we were in school, we knew that square is also a rectangle. So if you extend the same analogy, then why shouldn't an equilateral be an isosceles? That's one simple way of putting it. But we are going to delve a bit deeper into that. Okay? So, okay. So I'm assuming you can handle abstraction enough to be able to do that, just by visualizing. Who is the special one? Okay, so what is the specialty? Right, so there are 3 lines you will get, 3 folds you will get, right? So that is one way of looking at the specialness. There is another way. Right angled. Okay, so right angle has been vetoed out. Okay, so there is another way. One option is, yes, it is special because it doesn't have just 1 fold line, it will get 3. There's another speciality that this triangle has, the special one. We'll come to it. No, after the first fold, it doesn't remain isosceles. It will look like one of the triangles you get in your geometry box. Okay, which is a scaling triangle. Okay, we'll come to it. Okay. Okay. Now this may be a slightly harder thing to completely visualize. So what I will do is I will draw out. Okay. So if we take any triangle, okay, and we join the midpoints. Okay. We get 4 congruent triangles, each similar to the bigger original one. And now imagine you are folding this up, right? And if it was an equilateral, it will give you regular tetrahedron, right? So some of them will fold up to tetrahedron. Yeah, equilateral is the most boring case, right? Obviously, everything is symmetric, etc. So, you'll get the regular tetrahedron. And this is where it might help to draw out few triangles and try. Okay, now the question is there only one kind of isosceles? How many types of isosceles are there if we forget equilateral for the time being? Two? Okay, what are they? Okay, now, so you have right angled isosceles. Right? What does this right signify? Okay, it's a right angle, right? Now, that kind of acts as a border, as a fence between two other kinds of angles or even triangles. Okay, so obviously there is acute isosceles and there are right. Now, one of these also have subgroups, but I won't go into that right now, not right now. Okay. So see, there are at least three kinds. Okay. Yes, acute, there is a subcase of equilateral. Okay. Now, there is something special in these two. I mean, you can think of these as families of triangles, right? What is particular about the equilateral family and the right isosceles family? Okay, okay. I mean, that is kind of obvious, right? Because the smaller triangle you will get inside is similar to the big one, right? So that will happen in all cases. This is a very basic question actually. Exactly. So the angle combination is the same in each of this. Any right isosceles you pick, the angle combination is 90, 45, 45, whereas for equilateral it is 60, 60, 60, right? But the other two families are not like that, right? Now, you realize that this acts as a border between two groups. This also acts as a border between two groups. Okay? If you have acute isosceles, you can make it look like this, where the longer sides are taller or longer. I mean, the equal sides are longer. Or you can have it look something like this, where the equal sides are shorter. Okay? So you can figure out what it means for this angle here. You can find borders for boundaries for theta, theta between which and which. In this case, it will have to be, and in this case, okay. So two special families and both are kind of act as a border. Okay. So far we have got, let's say, 3, 4, 5 types of triangles. Okay. So which group is left out here? The scalene ones, right? Okay, and how many types of scalenes are there? Scalenes will all also have these 3 groups, right? So 3 scalenes. Let me write it maybe here. Okay. So you have a choice of 8 kinds of triangles. Okay. So if this was a workshop, I would immediately partition you and give each group 1 triangle or done something like that. Here I won't do that. So can you just pick your favorite triangles or whatever you want to play with and think visually what will happen if you try to create a tetrahedron. If you want to tear out a page and make a triangle and do it, you are more than welcome. Okay, it's flattening out. Yeah. Okay, so right isosceles flattens out, okay? All the sides, etc. matches, but it flattens out, okay? So this one doesn't work. And this we know definitely works, okay? So we know the situation for 1 acute and 1 right. So anybody wants to try what happens with an obtuse? What is happening with obtuse?
The side edge is not symmetrical. It is too high for the.
Okay. Now, is the problem with obtuse the same as the problem with right? There's different, okay. So let me now draw a big obtuse and show you exactly what goes on. Okay. Now it really, let's see. So this is roughly the midpoint, here is another, and here would be roughly the third one. Okay. Now we know that these angles are equal and these angles are equal, right? This is simple similarity kind of a thing. Okay. Now, what happens when you fold it? Since we have plenty of colors, let's utilize them. So when you are folding this, remember paper folding is basically like, reflecting. You are reflecting along the fold line. So if you reflect along this, you will get something like that. So this will be that, and right? Similarly, if you fold this one, you will get something like this. Okay? Now, if we call these two alpha and beta, okay, and so this is going to be, let's call it theta. So if you look at this part, then you see alpha and beta are getting taken away from theta in a way. Now, which is more? Are you sure alpha plus beta is more? Theta is obtuse, right? So that means 180 minus theta is less than, is acute, right? This is nothing but alpha plus beta, and so, and theta is definitely greater than 90, right? So what happens is, when you are trying to fold it, they won't even come together, they will stay apart, and that is why you will not have a tetrahedron, okay? Now, in acute, what happens is, this is the situation for acute, right? So you can fold them. If you fold them flat, they will form overlap. So if you fold them, they will meet some way, right? In case of which is the borderline case, it is equality. So everything matches up, but the tetrahedron is flat, no height, okay? Now, isn't this somewhat similar to the triangle inequality? The sum of two sides have to be greater than the third side? Eerily, okay? And that's a must for a tetrahedron of this kind. If you are thinking of making a tetrahedron with four congruent triangles as the four faces, then I don't know if any other arrangement is possible, you can explore. But it's a very eerily similar result, okay? Trust me, I ran into this accidentally, because one textbook changed from acute isosceles to equilateral in between two editions. So that triggered, this whole investigation and this neat result, okay? So just to sum it up, okay? Now, this is where, I was telling, the equilateral, which you pointed out correctly, triangle with multiple line symmetries, it's also the triangle which has a rotational symmetry, the only triangle, okay? Okay. Right? And yeah, it's the borderline case. So if we put it in terms of symmetry, then this is what we get for triangles, okay? And one box is empty. There is no triangle that has a rotational symmetry but does not have line symmetry, okay? Things change when it comes to quadrilaterals and get more exciting, complex and exciting, okay? So there are equilateral triangles. What about equilateral quads? Everybody knows that, right? Okay. Now the equilateral triangle also happens to be equiangular, as you have pointed out, right? What about equiangular quad? It is the rectangle. See? Nobody says that rectangle is equiangular. but it is. Okay? All triangles that you know have circumcircles, and for circumcircles, that is another place where the border, that right isosceles, right triangles act as a border between acute and obtuse comes out beautifully. If you take any acute triangle, the circumcenter will be inside the triangle. If you take any obtuse triangle, it is outside. Okay? And for right angle, it is the midpoint of the hypotenuse. Now that actually comes as a, corollary to a theorem. Semicircular angle is right angle. The other parts give these two. Okay? Though these dots are not always joined. In fact, there's a big application of this. If you are given a circle, big one, small one, whatever, which you cannot fold, and you need to mark the center. Okay? So this can be used to mark the center. Okay? Now, do all quadrilaterals have circumcircles? Yes? Sure? Parallelograms don't. I mean, unless they are rectangles, right? If they are, non-rectangle parallelogram with acute and obtuse angles, then they won't, right? Now, the ones that do have circumcircles have a special name. Cyclic, right? Cyclic quadrilaterals. Okay. So they have made it into syllabus. What about incircles? Any triangle will have an incircle. What about quadrilaterals? Parallelograms won't have, again. Okay. Rectangles won't have, right? Even if something is symmetric, it may not have. Rectangle is pretty symmetric, but unless it's a square, it won't. Okay? So this is something we are going to look into, and this is also something we are going to look into. Okay? Okay. Now this is easier to deal with. Okay? For cyclic, we know how it works. The if and only if condition. And in geometry, it is full of if and only if conditions. Okay? So this is very easy to prove. Any two-line or one-line how this can be proved? Just, yeah. Yeah, exactly. So if you have an incircle, so wrap a quadrilateral around it. Now from each vertex, let's call it these will be equal, these two will be equal. Right? So if you take AD plus BC, you will see that that has the same 4 pieces, one of each, as AB plus CD. Right? It's very easy to see that. Okay? So the question is it an if and only if condition? Is the reverse true? Sure? Then you have to give a counter example. So for parallelogram, these two are equal, these two are equal. Yeah. And rhombuses do have incircle. So this is how it goes. You can have an intuition, and if you intuitively feel no, it is not going to work, then you try to find a counter example. One counter example, that's enough to smash the statement. Okay, same thing. These two are equal, right? So unless all four sides are equal, this condition won't be satisfied. See, sum of these two must equal sum of these two. Yes, it does. All kites will have incircle. Rhombus is a special kite. So yeah, all kites will have. So when you have really sweated hard and couldn't get any counter example, then you start thinking of proof. Okay? In this case, you can actually prove it. I'll not go through the whole thing, but I'll give you the main idea. So suppose you have a quadrilateral. Nowadays, you can do one more thing. At least I do this kind of cheating throughout. There is a very, very good thing called GeoGebra. Okay? It's a free software which you will fall in love with if you start playing with it. So you cheat by trying to create something on GeoGebra, and you can vary angles, vary sides, etc. You can literally play around. So if you play around quite a bit, and it seems it works for all permissible angles. Okay, so for example, if you are talking about quadrilateral, I mean the angle has to be within 180 degree, right? So when you play around and it seems like it seems to be working, then you try to think of a proof. This is a legitimate cheating that you can do. Okay, and apparently people have discovered stuff in geometry after GeoGebra came in. Okay, so this is our quadrilateral, and we have AB plus C equal to AD plus BC. Okay, so what we do is we try to look at angle bisectors. Now, two of the angle bisectors will meet somewhere, right? So let us call that I. Now let us draw perpendiculars on the sides from there. So we'll join these two, drop this perpendicular and drop this perpendicular. Now, these two are congruent by angle, RHA, right? Or angle side, whichever. So, okay. Now, by same logic, these two are equal, right? Now, if we show, okay, let me give some names. So, now, the IF is the only one left out, right? If this is equal to IE or IG, then we are done, right? Okay, so let's say let us assume, okay, Because if we run into trouble, we can assume the other way. Okay. So if this is the case, then okay, then what can we say about CF and CG? See, these two are right triangles, right? Okay. So there is a Pythagorean triplet connection and IC is common to both. Right. So if IF is greater than equal to IG, then CF has to be less than equal to, right? Okay. Now if you play around with this, keeping these equalities, so here you have these two are equal, right? That is how far we have. Okay. Now with that, if you just expand out and play with it, you end up getting something like okay, I think I will be more comfortable working it all out. So AB plus CD, that is AH plus HB plus CD. So DF plus CF. Yeah. And that is equal to AE plus ED plus BG plus CG. Right? Now BG is equal to HB. And AH is equal to AE. Okay. Now CF is less than equal to CG. Right? So that means DF must be greater than equal to ED. Okay. So this is greater than equal to this. Okay. Now again, ID is common hypotenuse. So again, if you apply the Pythagorean triplet case for these two right triangles, you will get IF is less than equal to IE, right? So we get IF less than equal to IG, and no, IF was greater than equal to, right? But these two are already equal. Okay. So kind of works pretty neatly. Okay. Now let's get to the symmetry part. I don't know why incircles are not part of the syllabus. Okay, but they are not there. And it's a very legitimate question to ask. Circumcircle becomes cyclic, okay, fine. What about the incircle part? Now line of symmetry. Now suppose the quadrilateral is symmetric, mirror symmetry. So the line of symmetry has to pass through something, right? What are the choices? Midpoint of a side or vertex, right? So these are the two choices. Now, if the line of symmetry passes through one vertex, then what happens to the remaining vertices? It has to pass through the opposite one, and these two will be on either side. That means these two have to be equal, and these two have to be equal. So what are we getting? These two are equal. These two are equal. Adjacent, two pairs of adjacent sides equal. So that's a kite, right? Now, we have the line of symmetry is passing through the midpoint of one side. Okay? It's the line of symmetry is perpendicular bisector of one side. What happens to the remaining sides? Again, has to. Okay? So, this is perpendicular to two sides. It has to be a trapezium, and these two will have to be equal. Isosceles trapezium. Now, these two quadrilaterals are quite fascinating and very, very ignored. For kite, it is extremely unfortunate because kite is behind many of the constructions that we have all learned. If you think of an angle bisector, okay, behind that construction is kite and properties of kite. If you think drawing a perpendicular from an external point on a given line, again it's the kite behind the construction. Isosceles trapezium, even more ignored. Okay? So, this is what we get for quadrilateral. Okay? Now, in mathematics, you are not supposed to believe anybody. Okay? So, no matter teacher, Ramanujan, whoever, okay, you have to check for yourselves. So, whatever I'm saying, definitely don't believe it. The only thing where you can't argue is a convention. Okay? Those are arbitrarily set and one set cannot be changed. But otherwise, they can be. Even we'll already seen how definitions kind of change across time. So, we'll see that. There will be some reason behind it. So, what is arrowhead? Something like that, okay, that looks like this. So, if you have a kite, if you push the shorter sides inside, then it looks like an arrowhead. And here I am talking about the symmetric one. Okay? The other, if it is not symmetric, then it will look something like this. That's the concave quad. Okay? Now, any familiar quadrilateral missing here? Why is it missing? Yeah, so it is a rhombus and a rectangle. So it gets covered under both. So as far as this table is concerned, this small table, it doesn't have anything that makes it stand out of here. Okay. This is something that I would like you to ponder. No, right? I mean, because of the rotational symmetry, you would be able to rotate that one line of symmetry and get another line of symmetry. That was straightforward. Then there is a converse, of course. This is a little more involved, but I have faith you will be able to figure it out. Okay? Now, when I was playing with incircles and other things, this kind of duality came out quite nicely. Okay? See, on one side you will see sides, another side you will see angles. If you interchange angles and side, you know, kind of get them. It's quite interesting. Okay. And these are like hidden patterns, hidden treasures. The more you can spot them, the more fun it becomes. Those are also cues and clues. You could kind of figure out this is what, you know, I was using to construct that proof. Okay. So, IT is isosceles trapezium in short. I'll draw a better drawing. This is the best I could manage with the limitations of software. See, what happens is, so if you think of cyclic quadrilaterals, okay, and you add line symmetry to it, okay. Now, line symmetry means isosceles trapezium. So, automatically, now I really am going to use colors, yay. Okay, so this is cyclic, okay. So, if we add line symmetry and cyclic, see, if it is line symmetric, there are only two possibilities, isosceles trapezium or kite. Now, isosceles trapezium by definition will be cyclic, okay. So, if we have, let's say, this is, so here we have isosceles trapeziums. Now, if we think of incircle ones, again, incircle, line symmetry, that will be kites, okay. So, kites come in here. Then it turns out there is nothing here, right. So, this has to be modified to put like this. Can't be drawn as a circle, right. Because if a quadrilateral has a line symmetry, then it's either kite, in which case it will have an incircle. If it is a isosceles trapezium, then it will be cyclic. Now, can it be both? Yes. If you think of a kite whose equal angles are right angles, then this diagonal becomes the diameter and it will have a circumcircle. So, you can have a kite like this and all kites will have an incircle. That's pretty obvious. Similarly, you can wrap, depending upon the sides, it is possible to get a isosceles trapezium with incircle, okay. Not all will have, but some will. So, here there are special ITs and there are cyclic kites. Okay. So that is there. Is it possible to find something here? Yes. But that I leave as an open problem to you. Okay? Because I still haven't figured out how to draw one given specification. Okay. And the specifications are quite neat. See, we figured out what it is for this, right? And for cyclic, you need the sum of opposite. Well, they turned out to be 180 degree, which makes them equal also, right? So quite interesting. Okay, so looks like, you know, line symmetry is subsumed inside. There's nothing outside. So then let's look for rotational symmetry. Okay? So then you get something here. So this has rotational symmetry. Now, is there anything that will sit here? Any quadrilateral? Which one? Rectangle is always cyclic. The diagonals are diameters. Parallelogram, yes. Parallelogram is here. No line symmetry cannot wrap itself around a circle unless it's a rhombus, cannot wrap itself inside a circle unless it's a rectangle. So this one becomes rectangle, and here we get rhombus. Okay? And here we get square. Okay? Now this is where there was an issue. Yeah. How would you define an isosceles trapezium? Yeah. If you want to have a pair of parallel sides, they have to be opposite. They can't be adjacent, right? It can't happen, okay? So, this part is definitely has to happen. It has to be a trapezium, for heaven's sake, okay? This was the old definition, okay? Which is probably familiar to most of you, okay? Now, why do they need to specify that non-parallel sides? Because otherwise, it can become a parallelogram, which is not what you want. So you need to separate it from parallelogram. But then the problem is that it rules out rectangles. Now, I mean, this has a kind of nice symmetry, etc., right? Now, if you don't allow rectangle to be part of isosceles trapezium, then the whole graph, whole Venn diagram becomes really weird. Okay? And it doesn't make sense actually. So there's something to be done. So here's a suggestion. So one pair of sides are parallel. The other pair must be equal. Now, the moment you say the other pair, you are leaving it free whether they can be parallel or not. Okay? So, fortunately, when I was playing around with trapeziums a lot, isosceles trapeziums. I looked online and seemed like now rectangle is considered an isosceles trapezium. One less paper to write. Okay. The thing is, so the bigger question here is, if you want a set, a family, to be part of another family, what is the criteria? Why do you say that an equilateral is also an isosceles, or a square is also a rectangle, or a rhombus, etc.? It seems that this is the smaller one which you want to push inside the big one. So this will have some properties, right? The question is, does the elements of this set satisfy all those properties? Okay. So is there any property of an isosceles that the equilateral doesn't satisfy? Or is there any property of an isosceles trapezium that the rectangle doesn't satisfy? So this is kind of one main takeaway you can think about. Okay? So here is a set and we know what its properties are. Okay? And then there is another set which is considered outside. Do this have all these properties? Maybe some more. In that case, it goes inside. Okay? Now, you probably know this. This is not unique to math. You know Pluto, right? Not the Mickey Mouse character, the planet, or the X-planet. I mean, it lost its status as a planet. Right? So sometimes, definitions get revised, but somewhere you should be very, very clear, why did it change? What is the reason behind it? That's very, very important. Okay? So, 3 Blue, 1 Brown is a YouTube channel that I would highly recommend for you. It has undergraduate stuff, not baby stuff that I talked about. But this one, it actually illustrates how one particular property of rectangle was very important for solving this problem. Okay, which is actually a topology problem. Okay, and it's a topology problem with Mobius strip and the donut torus and all of those things. So pretty involved. Okay, the second one is probably a light read or whatever. Again, very highly recommended. It's called Lockhart Lament, a mathematician's lament by Lockhart. Okay, so it's his quote. Now, you may not believe that math is an art that can be considered an opinion, but when you play with it enough, then you get to feel that. And it's not Lockhart only who I think Russell also said something like that. Okay, Bertrand Russell. Okay, like comparing mathematics to the highest form of art, like sculpture or something. Oh, pressing the wrong thing. If you just put Lockhart Lament, you will get the PDF. Comes up. Okay. Can I take one moment to make an appeal? Okay. This is an appeal to you because you are undergraduate students, and secondly, because you are women. Okay. The thing is, the society still has some bias about women in math, so we are a minority. And we shouldn't remain a minority, first thing. Okay? women actually enrich math also. Have you heard of hyperbolic surfaces? So it's a woman mathematician who actually made it, helped in making sense of it, because women mathematicians can crochet, which men mathematicians didn't, male mathematicians, okay? And that really made a huge difference, okay? So hyperbolic surface, crochet, if you just search, there are 2 TED Talks, look it up, okay? And if any of you can crochet, try it out, it's awesome, okay? Why do you have, one line, 1 point outside? Why can you get infinitely many lines which are each one parallel to this one? If you can crochet, you will be actually able to see it and feel it literally. Okay. We are a country who had glorious past in mathematics, not just one Ramanujan, but we literally did, okay? I know one professor from ISI, I think he's still there, Amartada, who is actually, trying to figure out what Borahomihir did centuries ago, probably before Europe cracked those same formulas, same results, okay? Now, I don't think any of us can be very proud of the math education right now in our country, okay? Now, that is what I am personally trying to do, and there are some like us. But the thing is, people who really understand math and statistics rarely come and work in school education, okay? So my appeal to you is, whether you become mathematician or you take up any other profession where you apply your knowledge of mathematics, etc., if, teaching or the whole point of getting people excited in mathematics, just the way you find, interest and excitement in mathematics, if you want to spread that infection, okay, I'm deliberately using the word infection here, it needs to be spread. Please devote some time in school education. We really, really, really need you, okay? People who come into school education, they are largely about education theories, etc. Okay? And that might work. But math is a very, very unique thing. It starts at class 1 or even earlier. Science starts as science much later. Social science, history, all those things much later. So most classrooms may not, most school classrooms are extremely authoritarian. You have to follow these rules. But actually math is completely not like that. Completely the opposite. Every rule has to be justified. Okay? So most of the children don't even get a taste of mathematics. So since you are getting it, and obviously you are like it, love it, whatever, okay, please help in spreading the infection. And the reason I'm appealing to you as women is because when you stand in front of students, many girl children get inspired. And that is very important. Okay? The math world in many places is still pretty male dominant. So we need you. That's all.